We now discuss one of the most important topics in physics, which is Newton's law. We will start by discussing Newton's first law. Galileo Galilei made pioneering work in mechanics. The ancients believed that an object moved because it had a certain impetus, and as it moved, it ran out of this impetus. It eventually fell to its natural place in the universe. For an object like a ball made of material that seemed to be like from the earth, the natural place was to come to rest on the earth, which was thought to be the center of the universe. So to the ancients, this ball should roll down and eventually run out of impetus and will land here on the bottom because that's its natural place to go. These were not a crazy idea. There was a lot of observation that the ancients did, but what they didn't do was controlled experiments, and they didn't know about the idea of friction. Friction had been developed as a concept by Leonardo da Vinci, and we'll talk later about his role in pioneering the laws of sliding friction. Galileo knew about this work, so he knew he had to take friction into account. So he found that if he rolled a ball down an inclined plane, the ball would go a certain distance, maybe go up a little bit on another inclined plane, maybe to right here. He found that if he sanded and he put oil to smooth the inclined plane, he can make the ball roll a little further. If he did this over and over again, he eventually found that the ball would roll right back up here to its original height. And he found that no sanding or anything else would make it go further. So it was as if the ball remembered its original height. Now today we would say that it knows that the energy is conserved and that it wants to go back to where it puts all its energy back into potential energy. But those are concepts that were several hundred years after this. So we'll stick with what Galileo knew. Ball rolls to its same height. He found that he could back up this inclined plane, and if he sanded it appropriately, this ball would roll further and eventually go up the same height. Then he decided, well, heck, what if we make the inclined plane not as steep? He found again that after he sanded appropriately, eventually the ball would go up to the same height and no further. He could make the inclined plane even less steep. The ball would roll even further, back up to the same height. So the new law of physics is that a ball doesn't come to a rest or go to the earth, but it appears that balls always roll till they get to be the same height. Now Galileo then thought he could do a mental experiment. He could make this incline less and less steep until he made it basically flat. So in here you have another incline, this incline right here. And this ball is going to roll down here, and it will roll and roll and roll and roll until it gets to its original height. But it never gets to its original height. Consequently, the ball never stops. Now, Galileo had a good understanding of the fact the ball would never stop, assuming you could get friction, but he also knew some things about the earth. For instance, he knew the earth was round. This had been known from before the time of Christ, and educated people knew and could compute, in fact, the radius of the earth. So he thinks the ball is rolling on and on, but he thinks it's rolling on the surface of the earth and would go in uniform circular motion around the earth. Well, it turns out the problem there is he doesn't understand the concept of gravity. Now, Isaac Newton comes along, knows of Galileo's work. Isaac Newton knows about gravity. He's working on the problem of the moon going around the earth, and in fact he actually works that out and realizes it's the same as the force which causes a ball to fall. He's the person who really puts the concept of forces, the cause of acceleration, into this, which is why we're studying him. So he realizes, no, the ball will not naturally go around in a circle like Galileo has said. He chose it because of this idea of perfection in God and in the universe. He says what it should do is go in a straight line at constant speed. And this becomes known as Newton's first law of motion. So Newton's first law of motion states, a particle will continue to move in a straight line at constant speed unless acted upon by a net external force. You should put this to memory, and you should spend some serious time thinking about this law. It forms the basis of the conceptual way by which we think about how to attack problems. Now I've underlined some important words. Straight line. That's natural. Constant speed. Nothing in here says at rest. Rest is a special case. Nothing is required to make an object move. As long as it's going in a straight line at constant speed, nothing is required to make it move. Something is required to either slow down or speed it up or to change its direction. In short, natural is constant velocity. Now, it could be that the velocity could be 0. That could be a constant in a reference frame. But it also could be 30 meters per second in the x direction. And if it's 30 meters per second in the x direction, it'll go on forever at 30 meters per second in the x direction. Key point, this is for a particle. We're not assuming the thing can break apart. It's not shooting out cannonballs with cannons and so forth. We'll come back and talk about a more generalization of this in terms of a quantity called linear momentum in a later chapter. Okay, so for right now, we're considering things that don't fly apart. They're particles. That's what we've been doing ever since we started chapter 2. And we're called continue to move in a straight line, constant speed, unless, there is an unless, there is a net external force. So first is this idea of what forces that's a cause, this push or pull. Second, they have to be external to the body. They can't be inside. And last, it's not just one force, but it's the sum, the vector sum of those forces that can cause you not to move in a straight line or at constant speed. So what is Newton's law telling us? Well, as I was saying, the first thing it tells us the natural motion of an object. It's a straight line. At constant speed. And rest is just a special case. Rest is not the ultimate of what objects like to do. If the object's going 30 meters per second in the x direction, it will oppose trying to be brought to rest, in fact. It tells us when an object is accelerating, or not accelerating, and most important, the cause of acceleration. In the previous chapters, we've discussed how to describe motion. Now we're explaining why a particular type of motion occurs. It occurs because of this net external force. And we're going to need to have to find that external force in order to find accelerations. Now, people a lot of times say, well, you know, what is it really important? They really enjoy things that give them numbers. Newton 1 doesn't give you numbers. Newton 1 tells you how to attack a problem. And that's very important because students often say things like, well, I could work the problem, I just don't know where to start. Well, exactly. Newton 1 tells you where to start. Newton 1 does not give you numbers for A or F or anything else. If you're looking for number solving, that's what's called Newton 2. So it's very important, even though you don't get numbers from it, it's important in helping you know how to think and attack a problem. So that's the first of his laws, and it says there's this thing called force, which is extremely important, and so in the next video we'll talk about what we mean by force.